Most engineering structures are designed to be strong and stiff and change shape as little as possible. But Keith Seffin studies bistable structures, which are a little more dynamic.
Unlike a conventional structure, which is designed to be solid, strong, not move, a building or a bridge, these change shape in a very dramatic way to give you some other kind of property, some other functionality that gives you some purpose benefit that's different.
So I see you're holding what looks to be like one of those bracelets which kids play with sometimes.
Yes, called a flick bracelet. It's straight in one configuration. Flick it against your wrist, and it wraps around. So it has this very this bistable property, if you like, where it likes to be straight, but it also likes to be curved, as you can see.
I guess when it's straight, it's not actually perfectly straight. There's a bit of curvature on it. Is that important?
Yes, it is. If you were to take the plastic sheath off this, you'd end up with something that looks a bit like this. It's blue in colour, it's probably some alloy of steel, but you can see that it's got this nice, gentle curve across it, and in some ways looks like your sort of standard household tape measure, and in fact they're both essentially the same. And having a curve across it is key to this, because it's curved that way, straight this way, but when we activate the other shape, you can see that it's now flat across the width, but now curved along its length. So there's this kind of antagonism that's taking place, which is key to this shape-changing capability.
So it's got two stable states,
yep.
Either curved this way or curved in the other direction?
That's right, yes.
And is it this curve which is keeping it so rigid?
In this configuration it is. If it were completely flat that way, it would flop about. And as a tape measure, that wouldn't be very good, because you extend it, you don't keep things nice and straight. So that's very important, just for an ordinary tape measure, and indeed in this case. But in order for us to create the bistable property, what we can do, or what you can do at home with just an ordinary length of tape measure, is to take that and roll it up very, very tightly, possibly around a pen or a pencil, or your finger if you're feeling brave. And when you do that, you end up with something that is very, very tightly curved in this direction. And what that does is to, if you like, impart a sense of the shape in this curved configuration. It'll sort of spring back a bit, but that's natural for it to do so. But as you can see, although this was pre-prepared, it is the same process if you were starting with an ordinary piece of tape measure.
So when it was manufactured, it had the curvature in this direction, then you've added a stress to curve it in the other direction, so it's now got two stable states.
That's precisely what's happened.
This principle is not just used for toys. In nature, the Venus flytrap has a similar structure, so a small movement of fluid in the leaf triggered by an insect touching some trigger hairs can cause it to flip into its closed state. This traps the insect and gives the flytrap a fertilizer-filled lunch.
Another simple, fairly straightforward example is this slightly larger version of a flick bracelet, where in fact you'll see actually it isn't very much of it isn't flicking as such, but it looks very much like this. It's straight and it's kind of curved this way, but much more substantially curved, as you can see, to form something that looks almost like a tube. It's made of carbon fibre, and in being made of carbon fibre has this nice sort of property that not only does it like to be rolled up, but also extended at the same time, and you've got this region in between that sort of joins in the transition region. But you've got something which quite happily sits in a variety of extended or folded configurations. What's going on here, without getting too technical, is this there's a kind of an interchange of energy taking place. As you unravel the tube, there's a certain amount of energy released, and that's kind of gained exactly by the amount that you put into it when you roll back. So it's not desiring to be open or closed, unlike the flick bracelet or the Venus flytrap, where there's a lot of pent-up energy which is released instantaneously, thereby triggering a sort of dynamic performance. This is very, very, it's neutral behaviour, as we call it.
I guess this would be really useful if you had a great big long pole which you needed for some reason, and you wanted to store it in a convenient space, because great big long pole suddenly turns into a nice convenient roll.
Yeah, these were originally used and designed as robotic arms for remote handling in power stations, where you don't want to be anywhere near the radioactive substance, but you can sort of extend an arm with a sort of grabber in the end to manipulate uranium rods. And in more recent times, much longer versions of what we see here have been used by the British Army whilst on service, whereby they have a compacted version rolled up. They carry in their sort of backpacks, which is very easy to do, being carbon fibre, it's very lightweight. They can then extend it. So you can imagine this maybe being 2, 3, 4, 5 meters long. Put a camera on top of it, link it to a computer, and peer up into buildings or over dunes, that sort of thing, to get a sense of what's going on. So used as land periscopes.
Okay, so that's one use. What else is there that we could be using?
Well, just going back to the flick bracelet theme, I've got an example here of where, unlike a flick bracelet, which is very much longer compared to its width, this particular sheet is approximately, well, it's not square, but it's near enough. But if you could imagine taking several flick bracelets and linking them side by side, but alternating them as you do so, then you produce something which looks like a corrugated sheet.
I guess you couldn't just make the flick bracelet wider because it has such a curve.
Because you end up with a tube rather than a flat sheet as one of the configurations. So this is a bit like a lot of flick bracelets connected together, but in a continuous way. So we produce this corrugated sheet, and we have done our sort of deformation or sort of manufacturing process in this to create a structure which then rolls up a bit like a flick bracelet, as you can see here. So it rolls up into a nice tube, and it's quite compact, it's quite reasonably robust, and it can be unravelled again.
And when it's unravelled, it's quite nice and solid.
Yeah, it's very solid. You can sort of drop it. It's still there. But yes, so there you go.
So you've got a picture of a sort of computer screen on here. I guess the idea is you can get one of them modern flexible e-ink displays.
Yes, there's been a lot of development despite the recent surge in things like tablet computers, very solid, very sort of stable devices. There are developments towards making displays incredibly thin, electronic displays, so thin that you can bend them and twist them. That might create the sense of reading a book, for example, by having pages that look like real pages with ink. But they're very delicate structures, and what we're thinking here is, well, if you put this sort of structure in the back, which gives it some nice protection, you don't lose the sense of the flexibility or the ability to roll up by having one of our bystanders.
Like it means you can get a far bigger screen in your bag than you would do otherwise.
Or
in your pocket even, yeah.
Wherever, yeah, indeed. So that's kind of one idea that we're sort of thinking about.